Hello everyone and welcome to our presentation. First of all, let me thank you all for your presence here today. As you can see on the screen, our topic today is understanding blockchain, definitions, architecture, design and system comparison. This presentation is structured as follows. Firstly, blockchain introduction. Next, we will discuss blockchain definition and history, blockchain types and futures, then blockchain content and concepts and architectures, and we will discuss about blockchain comparison of different systems, and finally, blockchain conclusion. Chapter 1. Blockchain introduction. Blockchain technology is a decentralized and secure ledger system where transactions are recorded in a block linked together cryptographically, forming an immutable chain. It eliminates the need for intermediaries by allowing direct peer-to-peer transactions, verified and agreed upon by multiple network participants, using consensus mechanisms. Smart contracts automate agreements based on predefined conditions, while initially associated with cryptocurrencies. Blockchain finds application across industries due to its transparency and security. Challenges like scalability and interoperability persist, but ongoing developments aim to enhance its adoption and versatility. Chapter 2. Blockchain definition and history. DLT, or Distributed Ledger Technology, is a decentralized database system that allows for recording, sharing, and synchronization of transactions and data across multiple network devices or nodes. Key concepts of DLT include decentralization, where each node returns a copy of the entire ledger, ledger immutability, consensus mechanism for transaction validation, and cryptographic security. Different types of DLT, such as blockchain and DAGs, support for smart contracts and various use cases in industries like supply chain management, healthcare, and decentralized finance. DLT, particularly blockchain, gained popularity with Bitcoin, but its potential extends beyond cryptocurrencies to offer secure and efficient systems in multiple sectors. History of blockchain. The timeline of blockchain's evolution is marked by significant milestones and key innovations. 1982, David Hume introduced a concept resembling blockchain in his PhD thesis. 2008, Satoshi Nakamoto unveils Bitcoin, a purely peer-to-peer electronic cash system, introducing the term blockchain as the distributed ledger for Bitcoin transactions. 2015, the Linux Foundation launches the Hyperledger Project, an open-source initiative for enterprise-grade blockchains, including various frameworks like Hyperledger, Piso, and Fabric, and tools like Avalon and Celo, and libraries like Quill. Bitcoin and Ethereum representing public blockchains allowing open participation without permission. In contrast, the Hyperledger ecosystem includes multiple private blockchains, requiring participant verification before network entry. Definition of blockchain. Blockchain is a decentralized and distributed digital ledger technology that records transactions securely and transparently across a network of computers. It operates as a chain of blocks, with each block containing verified and encrypted transactions, linked together using cryptographic techniques. Key characteristics of blockchain include decentralization, immutability, consensus mechanisms, and cryptographic security and transparency, making it applicable in various sectors beyond cryptocurrencies. How the blockchain works. A diagram that shows how a transaction is completed using a blockchain. The process of completing a transaction using blockchain is as follows. 1. A transaction is requested, such as sending money to another person. 2. The transaction is broadcasted to the network of computers that are part of the blockchain. 3. The network validates the transaction using cryptography to ensure that it's legitimate. 4. If the transaction is valid, it's added to a new block. 5. The new block is added to the existing blockchain. 6. The transaction is complete. Once a transaction is added to the blockchain, it cannot be changed or deleted. This makes blockchain a very secure way to store and transfer data. Blockchain workflow. The workflow of a typical blockchain involves transaction initiation, propagation, and validation across the network. Valid transactions are stored in the mempool or transaction pool, awaiting inclusion in a block. Miners or validators compete to create a new block by solving a mathematical puzzle or reaching consensus. The new block is broadcasted to the network, verified and added to the blockchain to have consensus. The ledger is updated across all nodes, and miners or validators may receive rewards for adding a block.
In this chapter, we are going to find out some types and features of the blockchain. In existing literature, our blockchain systems are broadly divided into two types. The first one is referred to a public, open, or permissionless blockchain, while the second is referred to a private, closed, or permissioned blockchain. Let's start with the first type. A permissionless blockchain, also called a public blockchain, is a permissionless and unrestricted recording system. Anyone with internet access can connect to a blockchain platform to become a verified node and a member of the blockchain network. A node or user within the public blockchain has the authority to access the current and previous records stored within the system. Participants are allowed to view updates on the blockchain and have a permission to read the blockchain data. The most popular public blockchain are Bitcoin and Litecoin. Public blockchains are typically secure as long as users are well aware on the rule and security protocols. It becomes risky only when individuals fail to adhere to security protocols correctly. There are many advantages of this type of the blockchain, like inclusivity. Anyone can join the public blockchain. Trustability. All transactions are recorded in an inalterable manner and timestamped. This enables members to view the entire transaction history and eliminates any possibility of fraud. Trust and security. Permissionless blockchains foster greater trust and security due to the absence of the central authority that could alter or become the target of an attack. And we have a safeguarding against malicious applications. It provides a means to protect clients from the malicious applications. And the drawbacks of this category, we find a scalability challenge. Permissionless blockchains must manage large user bases and high traffic volumes, and the presence of the malicious actors. Since anyone can join permissionless blockchains, there are always a risk of encountering malicious actors on this network. Permissioned blockchain. An entity won't have access to a permissioned blockchain unless pre-approved by a designated authority. Permissioned blockchains are entirely different from the permissionless one. To participate in the network, a specific access must be guaranteed by the administrators. There are three types of the permissioned blockchain. The first type is a private blockchain. In this type of blockchain, access is restricted, allowing only invited and authorized users to execute transactions. The second type is a consortium blockchain. It's a type of blockchain managed and operated by several organizations or entities. It operates as a permissioned blockchain, meaning users need to be invited and authorized before accessing the network. The last type, called hybrid blockchain. It's a fusion of private and public blockchains. This type leverages features from both, allowing for a structure based on a private authorization and a public consensus system. Users can control who gains permission to access specific sets of data in the blockchain. There are many advantages of this type, including scalability and speed, flexibility, and administrative structure. I mean by scalability that permissioned blockchains are managed by an entity with a certain level of control over validator. Upgrades can therefore be implemented relatively easily. And I mean by administrative structure, authorized blockchains can also align with the administrative structure. From the drawbacks of this type, we find the complexity and less anonymity. Permissioned blockchains tend to be more complicated in their setup and management. Blockchain features. There are many features of the blockchain technology, but we mention 6 main characteristics of the blockchain that make it popular. Blockchain technology employs the concept of decentralization. Decentralization is the process where there is no centralized authority to plan or make decisions to execute a transaction for an organization. Transparency. When we examine the transaction history in blockchain, only the pseudonymous identity of the user is represented instead of his real identity. Immutability. Once a transaction has been initiated and the data has been inserted to the blockchain, it cannot be changed or deleted. Additions made to the blockchain are permanent and immutable. Peer-to-peer networks are interconnected collection of all nodes where the total workload is distributed among all participants, known as peers. However, these peers are distributed and decentralized. Distributed ledger. The database of each transaction is broadcast to all nodes in the peer-to-peer network, and an identical copy of the database is maintained in the ledger of all nodes. Irreversibility. This is the process where once a task is executed, it cannot be traced back. In blockchain, the variable length of data or information is passed through a hashing function to obtain a fixed and encrypted output.
Chapter 4: Blockchain Content and Concepts. Nodes in a blockchain network are individual devices that maintain the network and contribute to its function and security. Nodes verify and validate transactions, propagate them across the network, and create and validate blocks. There are different types of nodes, including full nodes that maintain a complete copy of the blockchain, lightweight nodes that rely on a full nodes for a specific data, and many nodes that require power. Nodes play a role in the consensus mechanism, network health, and security of a blockchain network. Miners in a blockchain network, particularly those using proof of work, validate transactions, create blocks, and maintain blockchain security. They verify transactions, group them into blocks, and solve complex mathematical problems to add blocks to the blockchain. Miners are rewarded by cryptocurrency tokens for their efforts and contribute to network security by preventing double spending and ensuring ledger immutability. In PoW-based blockchains, miners collectively participate in consensus by computing to add blocks and achieve agreement on transaction and block validity. Blocks in a blockchain store verify transactions and are linked together in a chronological chain. Each block consists of a header and a body. Blocks are immutable and tamper-resistant, ensuring the integrity of recorded transactions. Block size limitation affects scalability and transaction throughput in different blockchain networks. Consensus algorithms. Consensus algorithms are crucial for blockchain networks to agree on the ledger's state and validate transactions. Prominent consensus algorithms include proof of work, proof of stake, delegated proof of stake, proof of authority, proof of burn, and proof of space-time, and proof of capacity. Each algorithm has its strengths and weaknesses impacting factors like security, decentralization, and energy consumption, scalability, and participation requirements. Hybrid consensus mechanisms combine elements of multiple algorithms to achieve better scalability, secure, and decentralization. Proof of work versus proof of stake. We have a table comparing and contrasting two consensus mechanisms used in cryptocurrency. Proof of work is the traditional method used by many cryptocurrencies, including Bitcoin. In proof of work, miners compete to solve complex mathematical puzzles in order to validate transactions and add new blocks to the blockchain. The first miner to solve the puzzle wins the right to add the block and it's rewarded with cryptocurrency. A proof of stake is a newer consensus mechanism that is designed to be more energy efficient than proof of work. In proof of stake, validators are chosen based on the amount of cryptocurrency they hold. The validators are responsible for validating transactions and adding new blocks to the blockchain. They are rewarded with cryptocurrency for their work. The proof of work is more secure and decentralized than proof of stake, but it's also slower and more energy intensive. Proof of stake is faster and more energy efficient than proof of work, but it's less secure and more centralized. Blockchain smart contracts. Smart contracts are self-executing contracts written in code that automatically enforce and execute predefined conditions on blockchain networks. They are written in programming language specific to the blockchain network, such as Solidity for Ethereum. Smart contracts enable decentralized execution, immutability, and transparency, reducing the need for intermediaries. They have diverse applications in finance, supply chain management, healthcare, voting system, insurance, and gaming, but face challenges related to security, auditing, legal implication, scalability, and complexity.
In this chapter, we are going to explain a very important notion in the blockchain systems. It's the architecture of the blockchain. The design of blockchain systems is based on an architecture in layers. The different layers of the blockchain are grouped together to guarantee shooting security and scalability. In fact, blockchains must be very secure because there is no central authority. In addition, they must be scalable to accommodate the growing number of users across the system global. Layers emerged because of the need of scalability while now excellent security. This figure represents the layered architecture of the blockchain. It's made up of 6 layers linked to each other in order to maintain a better quality of service. Hardware layer. This is the lowest layer of a blockchain system. Hardware can make calculations such as cryptographic hashing more efficient, provide additional security for storage and environmental computing, and so on. This layer is nothing more than a vast network of devices communicating and exchanging data among themselves. In fact, this is how a distributed ledger was born. A data storage layer. This is the most crucial part of a blockchain system when it comes to storing data, preserving it against the modifications, and making it traceable. This layer is also responsible for ensuring the availability and the durability of the data. Communication layer, also known as the network layer, propagation layer, or peer-to-peer layer, is essential for any blockchain system. It requires a mechanism to disseminate transactions and blocks among the participants. This layer manages communication between nodes, handling nodes discovery, identification, transaction, block production, and block propagation. The peer-to-peer architecture of the blockchain enables nodes to reach consensus on the legitimacy of transaction. The transaction itself on the blockchain is carried out by nodes. Data manipulation layer, known as consensus layer. The primary responsibilities of the data manipulation layer include updating the blockchain and providing blockchain data search functionality. Since an update must be a coordinated decision in a decentralized environment, with the lack of trust among individual participants, the consensus protocol plays a central role in all blockchain systems. Contract layer is a crucial element responsible for managing smart contracts, self-executing agreements with predefined conditions written in code. This layer oversees the development, deployment, execution, and interaction of these contracts within the blockchain environment. In essence, blockchain systems provide the ability to define contracts, to create and enforce rules among the network participants. Different blockchain systems might use various methods to devise contracts based on their application domain. Application layer is an abstraction of the application built on a blockchain system. While its specific design goes beyond the scope of a blockchain system, it defines the requirements that a blockchain system must meet. The application layer ensures the deterministic nature of the blockchain. It contains the programs that users employ to communicate with the blockchain network. These facilitate communication between consumer devices and the blockchain.
In this section, we explore different blockchain systems and their variation. To delve into the technical specifics of blockchain technology, we will scrutinize four unique systems. Bitcoin remains relatively unchanged, Ethereum exhibiting a substantial update, while Hyperledger Fabric evolves with a new version. Each era is currently the best documented version. Bitcoin system is a distributed peer-to-peer network. There is no central server or control point, and all participants in the network are equal pairs. The participants referred to as the Bitcoin nodes in Bitcoin terminology. These nodes can be categorized into two types, full nodes and lightweight nodes. The full nodes perform exclusive rules, while both of them play a crucial role as the creators. That implies the separation between entities is more blurred in Bitcoin, same thing in Ethereum. While Ethereum and Bitcoin share some fundamental entities within the system, Ethereum introduced several additional fundamental concepts and mechanisms that Bitcoin does not possess. The most important of these are the concepts of gas and fee. Ethereum offers various types of transactions, some of which involve Turing-complete programs. This is where the role of the gas comes in, measuring the budgets of execution units or fee. These fees are paid by the creators of transactions. Unlike Bitcoin and Ethereum, the Hyperledger Fabric, designed for private blockchain networks, does not have mainers. The entities and their responsibilities differ from Bitcoin and Ethereum. An essential distinction lies in the fact that Hyperledger was established within the Linux Foundation. The three entities of Fabric: clients, pairs, and orders. The client is a computing device from the application layer running on the blockchain, serving as a transaction creator. The pair is validate and authorizes a member within the Fabric network. The orders is specialized computing device. Similar to Bitcoin and Ethereum, it operates as permissionless blockchain but distinguishes itself by organizing transactions into bundle rather than block, and achieves higher throughput than Bitcoin and Ethereum by grouping transactions into directed acyclic graph, different from sequential chain organization. Blockchain systems can be classified into 6 distinct layers: hardware, data storage, communication, data manipulation, contract, and application. In the following, we will examine the characteristic and implementation of each layer within the 4 chosen blockchain systems. For the hardware layer, we will discuss 3 features: limiting resource, crypto puzzle solving mechanism, and security hardware. The limiting resource in Bitcoin is the processor, in Ethereum is the memory bandwidth, in Fabric is application dependent, while in IOTA is the processor and network bandwidth. The crypto puzzle solving mechanism in Bitcoin is ASIC processor. In Ethereum is GPU processor. IOTA use Gen processor, while Fabric does not contain crypto puzzle. The next feature is security hardware. Bitcoin and Ethereum both use the hardware-based trusted execution environments. In IOTA, no additional hardware. We move on to the next layer, data storage. We will discuss in this layer three features. The first feature is the state tracking approach. Bitcoin and IOTA both use UTXO approach, while Ethereum use arbitrary state method, and Fabric doesn't have a default state tracking, giving developers the freedom to implement their desired mechanism. Let's move to the next feature, maximum block size. The protocol has set it at 1 megabyte in Bitcoin, while Ethereum use the concept of gas limit. Fabric based on the application requirements, and IOTA use the concept of Paggy, where the transaction without limits. The last feature, RAM storage. We mentioned three critical data structures maintained in Bitcoin memory: Miracle Tree, UTXO cache, and block index database. Ethereum use a cache of Miracle Patricia trees, while IOTA incorporate a Jungle accelerator. The three are used in different way by both Bitcoin and Ethereum. Bitcoin utilises binary miracle trees and dynamically generates miracle trees in memory as needed. These three are instrumental in optimizing bandwidth consumption during transaction verification. We move on to the next layer, communication layer. The entity forming the network in Bitcoin is the full nodes. It's same in Ethereum and IOTA, where Fabric relies on the pair to form a peer-to-peer network. Let's move on to the next feature, communication protocol. Bitcoin use inventory and gate data. Ethereum utilizes a block hashing and the gate header. IOTA use a push-based propagation, while Fabric utilizes the ladder retrieves blocks from the orders and push gossip. Will average time for a full node to receive a block in Bitcoin about 12.6 seconds. On the other hand, in Ethereum about 109 milliseconds. It's very faster than Bitcoin. We move to data manipulation layer. The protocol used for updates in Bitcoin is the longest share rule. Ethereum used the greatly heaviest observed subtree protocol, while IOTA utilized directly a cyclic graph using tip selection algorithm. Fabric used a raft implementation based on the raft protocol. Next feature refers to how many transactions a system can process over a period of time. In Bitcoin, 3 to 7 transactions per second. Ethereum approximately 15 transactions per second. IOTA the range of 45 to 50 transactions per second, while in Fabric is not fixed. To mitigate the attack denial of service, Bitcoin used the proof of work, while Ethereum utilized the proof of work and gas limits. IOTA used the probabilistic confirmation. Fabric utilized the raft protocol. We move to the last layer, contracts layer. The type of contract used by Bitcoin is scripting system. On the other hand, Ethereum is contained smart contracts. It's the same in Fabric, but organized as the chain code.
Chapter 7 Conclusion. In summary, the presentation provided a comprehensive overview of a blockchain, covering definitions, architecture design principles, and system comparisons. Blockchain, a decentralized ledger, offers potential transformations in transparency and security across industries. Its architecture, relying on a block and consensus mechanisms, ensure data integrity, while design principles like cryptographic hashing. As the blockchain continues to evolve, its transformative potential becomes evident, requiring a thoughtful and informed approach for its integration into various sectors to redefine trust and efficiency in our interconnected world.